Hello, in this video I'm going to look at polynomials and their graphs. Now, we have that we'll start with a function such as x cubed, and we can see that the degree of this is positive and it's odd, and we see that the coefficient is positive in either case because we have that this is kind of like a 1 right here in front. But looking at the graph of the equation, we see that it has a particular type of end behavior, and that's the way that we'll kind of describe it. So the first thing that we could look at, for example, of this function is looking at the domain, which in this case would be all real numbers from minus infinity to infinity. And then we have that if we look at the range, well, the range based on this graph is also from minus infinity to infinity. And remember that when we looked at functions, we looked at their graphs from left to right for the domain, and we looked at from bottom to top for the range. Now notice that, in this case, we already had the graph. And if we didn't have the graph, for example, well, then you would have to probably go through the process of, for instance, figuring out some particular points, and we can look at, some in particular, such as like if we wanted to know what is f of -2, well, in that case, that would be -2 to the third power, which is -8. So in that case, we have the ordered pair -2, comma, -8, which in this case we can see that that's right about here. No, sorry. That's right about here, down over here. That's this point right here. And similarly, if we want to find f of -1, well, that's just -1 to the third power, which in this case is -1. So we get the ordered pair -1, comma, -1. And then you know that f of 0, that's just going to be 0 cubed, which in fact is 0. So that gives us 0, comma 0. Now, notice that, we could plot other points such as like 1, 2, 3, and so on. But notice one thing in particular, that the points are actually just getting reflected over the origin, so y equals x, and it's just flipping the points. So, for example, f of 2, well, it would be -8, but since we're reflecting, then it's going to be +8. So we have that the ordered pair would be 2, comma 8. Now, you could technically also just say, well, 2 cubed is 8, and similarly, I skipped f of 1, which 1 cubed is just 1, so that's going to be 1, comma 1. And then, if you want to find f of 3, well, then that's going to be basically 3 to the third, which is 27. Which, I mean, if you take the cube root of 27, that's going to be 3 in either case. Okay, so, and yeah, we have that this would be 3, comma 27. So here we have a lot of points that we could plot, such as like -2, -8, -1, comma -1, 0, 0, 1, comma 1, 2, comma 8, and then also 3, comma 27. Now, in particular, I think that the goal really is that if we have any polynomial function, that we would be able to describe its behavior and then find a rough sketch of its graph. So let's think about this. So a polynomial is essentially a function of which it's given by, let's say, like an x to the n plus an minus 1 x to the n minus 1. And then basically you have that would be down to a1 x plus a sub 0. Now these coefficients are just real numbers, and they're constants in either case. And the degree of this is n. But let's say that, for instance, that we just focused on the first term. Okay, so the first term. Well, in that case, that's going to help us in determining the end behavior of any polynomial. So for instance, if we have that, we're going to say, now, for the purpose of, looking at the end behavior, let's just call it A for now. Because in actuality, it's just a constant really, right? So I want to look at what would happen if A is positive and N is, let's say, odd. So here we'll think of like a set of cases. So my first case will be, what if A is positive and what if N is odd? Well, in this case, if you look back to the cubic function, you might have noticed that the end behavior, it reflected over the origin, which in either case meant that we had something like this, where it falls to the left, but then you have that as x got bigger, then it just rises to the right in this case. So we have that this would be roughly the end behavior of this polynomial in this case. And you can verify that using, y equals x cubed in either case. So, we can say like, e.g. x cubed, for example. Now, if, for example, you have that A is negative, but N is odd, well, in that case, it's pretty much the opposite now, that it's just going to now rise to the left, and then it's going to fall to the right. So in that case, that's like saying if you have negative x cubed, for example. And, it helps, if you see like a rough sketch, for example, because this could be our function, and this is kind of like what it would look like, for example. Now, the other cases that you may have for describing behaviors of polynomials is, what if, for example, the constant was positive and the n is even? Now, in this case, if you want, think of, for example, x squared. X squared is one of the most common shapes of a graph that is parabolic, or in either case, we could just say, well, I know that, it rises to the left and it rises to the right. And, we can verify that using our calculator and just say, well, if I was going to graph x squared, well, in this case, x squared, if we go ahead and let's do zoom standard. Okay, so we can see that the graph of the parabola looks something like this, and that's doing that because I may have been using this for another class, perhaps. So let's just make that a solid line. Yeah, there we go. And then we go back to here. Let's see. Okay, so I don't want to color it. Okay, and then I just click OK. Okay, so then go back to graph. Okay, so there we go. So we have our parabola, and we see that it rises to the right and it rises to the left. Or in either case, like if we know the domain of it, then in that case, that's going to give us, well, the range actually, right? Yeah, so if we know the range of it, then that tells us that we'll know the end behavior of this. Okay, now similarly, if we were to look at where the constant is negative, and then you have that n is even, well, in this case, the end behavior is completely opposite, because we have that it's going to be now falling to the left, and it's going to be falling to the right. And the easiest one to think of is basically just negative x squared, for example. So we see that basically the end behavior of this function would be that, yeah, that it basically goes to minus infinity. And similarly, you have that it just goes to minus infinity, or it's coming from minus infinity, if that makes more sense. Because, yeah, you can think of it that way. Now, if you needed to, let's say, for example, describe the end behavior of a polynomial, well, you know, like if you had a polynomial like g of x equals to, let's say, negative x cubed, and this was plus 11x squared plus 32x minus 24, then in this case, it is of value that you would recognize that this is a cubic polynomial, but more or less, you just have to determine, you know, like what are the coefficients. So like, for example, you're looking for the leading term, of which the leading term is the negative x squared, which means that the a is equal to negative 1, which is less than 0. But then you know that the degree is 3, which in this case is actually odd. So we have that this is an odd degree polynomial with a negative sign. Now in this case, if we wanted to know basically sort of like the end behavior, then in that case we would see that, well, for a negative odd, then in that case it would be the complete opposite of x cubed. So in this sense, just think of negative x cubed, because that's the behavior that it's going to mimic, essentially, where you have that it rises to the left and it falls basically to the right. Now, if we were going to look at this in our graphing calculator, we could say, well, we have negative x to the third power, and then that's going to be plus 11x squared. And then, yeah, plus 32x. And then minus 24. Okay. Now, in any case, for this one, let's say that we want to give it a window, because I don't think that if we graph this, it's going to be big enough. So let's do minus 20, and then to 20, and in this case, let's see. Okay, so maybe for this one, we'll just say minus 50, and then for the maximum, we'll put 500. Let's see. Okay, so we see that this is our graph of our equation, and if you want to zoom out just a little bit, we can. So that way you can see that the graph looks something like this. Okay. Okay. Now, notice that in either case, the end behavior is completely correct in the sense that it does look that it's rising to the left and it's falling to the right. But look at these peaks. We have one right here, one right here. We have x-intercept, x-intercept, x-intercept. So if we wanted to find, for instance, the zeros of the polynomial, basically we would have to, for example, just find one and sort of use that, well, we can tell that it switches signs, and we just give it kind of like a guess. And it's showing me that one of the zeros of the polynomial is 0.62. But similarly, you do the same thing for this one and this one as well. But another point that we have is essentially this maximum. of which in this case we could say, for example, that this one is to the left, and this one is to the right. We hit enter, and we see that the maximum is 8.57 and then 4.27. So there's our maximum. Of course, you would have to do the same thing if you wanted to find the minimum, where you look at the calculator, well, the sketch of the graph, right? And you would find that minimum now, and it's kind of like the same thing where you kind of have to show sort of like a sign change because you're going from negative to positive, so that's kind of the thought process to that. And we see that it's barely seen, but sorry, negative 1.24 comma negative 44.85. Now consider this, like, when does this make sense? Well, it makes sense more or less in real-world applications where you're trying to either minimize or maximize something, which in our case we've been looking at profit, revenue, cost. But it would be the same thing if you're trying to maximize, say, volume, area, and so on. So this would be very helpful and is actually explored specifically like in courses like calculus and even calculus 2, for example. Now, continuing with, for example, like looking at, how would one sketch the graph of a given polynomial, and that's kind of like where we'll go from here and saying, well, for example, let's say that if we had a function such as x minus 1, and then you have x plus 1, and then you have x minus 2. Now, in this case, I know that if I was going to multiply this out, I would get, for example, that the leading term is x cubed, which basically means that I already know that it's going to fall to the left and it's going to rise to the right. But I also know, looking at this, that there are x-intercepts, for example, because you have x minus 1 times x plus 1 times x minus 2, and these all equal to 0. Well, in either case, if you set each of those equal to 0, then you're going to get 1, negative 1, and 2. So that means that we have the ordered pairs negative 1 comma 0, we have 1 comma 0, and then we have 2 comma 0. Now in that case, though, note that all of these, because they're all single zeros, then in that case we would say that they have a multiplicity of 1, which means that essentially they will go right through these ordered pairs. And think of it this way. Okay, so if you have an ordered pair with a multiplicity of 1, and you know that the graph passes through there, then in either case it would look something like that. But if you had more or less where maybe that it was a multiplicity of 2, then in that case it would have to mimic the behavior of, like, say, a degree polynomial 2, which is a parabola, sorry. And in either case, though, if anything has an even power, it's actually just bouncing right off of the graph or the x-axis. So we have that in this case, this would be like if it's squared. But if it was cubed, well, that's kind of interesting because it means that it kind of like wiggles through the x-axis, if that makes sense. So essentially we have kind of like 3 cases where it passes through the graph, where it kind of makes a turn, or it goes straight through, or it bounces off the x-axis. In either case, it's all has to do with the multiplicity in either case. So, that's just like a quick little lesson in terms of like looking at, how a graph will pass through. So, in either case, I think that what we can do is also look at, well, what is f of 0? f of 0 is 0 minus 1 times 0 plus 1 times 0 minus 2, which in this case would be positive 2. So we have that the graph of this, it passes through 0, comma 2, right? Okay, so here we can probably just graph where we'll just make like a rough sketch where we plot 0, comma 2, and we have to plot 1, comma 0, and we have to plot, what's the other one? Negative 1, comma 0, and the other one, what was the other one? Okay, so the other one is 2, comma 0, right? Okay, so 2, comma 0. Okay, so here it looks that we just have to kind of make the graph go kind of something like this, where it passes through and it comes back up. So that shouldn't be too bad. And this is a rough sketch. Okay, so it is true that, for example, that we are just going to look at the end behavior, or if we look at the end behavior, we can see that this graph has a domain from negative infinity to infinity, but look at the range. The range would be from minus infinity to infinity as well. And notice that we have two peaks. We have one right here at 0, comma 2. There might be another one though, because it's likely that maybe the peak is a little shifted, but in either case, it's getting us thinking about, what the graph could look like, for example. And let's say that we wanted to use Desmos to graph this. And our graph is going to be x minus 1 times x plus 1, and then x minus 2. So here, and notice that the graphs look very similar. For example, we have that the graph of our cubic polynomial, we see that it falls to the left, and we see that it rises to the right. Now notice that if we click on here, here, and here, we have basically these x-intercepts, for example. And yeah, sure enough, I was kind of off on my sketch, where I see that the maximum is a little to the left of it, and the y-intercept is at 0, comma 2. Now, I probably should have used a better judgment where I thought about how it has to rise, but I didn't know where it fell, basically, in this case. So things like this we can account for in things like calculus, or just using continuity and things like that, in saying, how do we know that it's going to kind of make this little turn right here? So in fact, there is a turning point, or a maximum, at 0.22, comma 2.1, and then here, down over here, we have this minimum of 1.5, comma negative 0.6. Okay. And in either case, if we were going to, let's say for example, like, I don't know, maybe we look at it from 0 to 2, then in that case it's different. It's that we have a maximum at 0, comma 2 now, and then in this case we have a minimum, well, we call them absolutes, right? We call them absolutes at 1.5 in either case. Now, the goal, I would say, for example, would be that, what if we were given any polynomial and we wanted to know its end behavior, or we wanted to know, for example, like its domain and range if it was restricted, for example. But in either case, the main thing is that if you know the degree, if you know the coefficient, And in that case, finding the x-intercepts and y-intercepts can be found if you just set the function to 0 and then solve from there. But the problem with that is that the polynomial, in this case, would need to be in its factored form. And if it's not in its factored form, that means that we would have to either factor or we would have to figure some other way of rewriting a polynomial, which in either case, goes back to like finding rational roots of polynomials using synthetic division, or in some cases, like once you are looking at functions in terms of their behavior relative to calculus, then that's kind of the whole point of courses like that, is to find x-intercepts or even factoring forms of polynomials using calculus methods. But in this case, like, we're only just interested in rough sketches of polynomials and their graphs, and then looking at their domain range, their turning points, and then also like where they might increase, decrease, etc.